And as for the program today, we will start with our great colleague Pere Vazquez from Universitat Politécnica de Catalunya. And let me briefly introduce him. So Pere Vazquez is an associate professor in the computer science department at the Universitat Politécnica de Catalunya in Barcelona. He is member of the Research Center for Visualization, Virtual Reality, and Graphics Interaction. And he has been working in the areas of scientific visualization and computer graphics for more than 20 years now. His main interests are in the visualization of biomedical models, the development of novel visual analysis techniques for large data sets, as well as interaction in virtual reality environments, which is actually one of the topics of today's talk from him. After graduating in computer science, he obtained his PhD in software in 2003 at Universitat Politécnica de Catalunya in Barcelona as well. So Pere, thanks a lot for accepting our invitation. We all are very looking forward for your talk, and the stage is yours whenever you are ready. Thank you.
Okay. So thanks a lot for inviting me. Let me share. I hope you see. And yes, it's going to start at some point. Okay, so I'm going to talk about VR and AR in biomedicine, but this talk, since it's, well, you know, 30 minutes, I will be able to just give you a small glimpse on what's going on and what are the possibilities in this area. Okay, so first I will talk about virtual reality, then augmented reality, and then I will close with very quick conclusions. Okay, so let's start with virtual reality. So what's virtual reality? So according to, for example, this definition by Rowell, virtual reality is a computer interactive simulation from the point of view of the participant in which the received sensorial information is augmented or substituted. Basically, from here, we can take that there are three important components. One is the interactive visualization. Interactive visualization means that the virtual environment, so the virtual world, must react to the user interactions. And this requires something that it's very important, which is a speed. A second important thing is the implicit interaction. If we are substituting the real world for a virtual one, we want the user to be able to interact with the virtual world as close as possible as he or she would do with the virtual one. So he or she should be able to change point of view and, of course, as much as possible to interact with the virtual world. And then there's also this third thing, that it's sensory immersion. So you have to provide things that let the user feel that he or she is in the virtual environment. So the first thing, and what everybody provides, is stereo, but we can also provide other stimuli for other senses, just tactile or olfactory. If we are able to do it very, very smartly, the user will have the feeling that he or she is exactly in the virtual world and not in the real world. And what are the advantages of working in virtual reality or having a virtual reality environment? So one of the big advantages is that we have 3D perception. So we can communicate, in contrast to what we do with desktops, we can communicate the 3D positions of the objects, and therefore it can lead to a better understanding of the shapes or positions of everything, such as molecules or 3D or organs, and so on. There's another advantage is that typically virtual reality environments provide a large screen, which can be virtual. I mean, maybe the screen is limited, but if I rotate, I see new things. So in theory, at least, there is more space for providing visual data. Then also, as I mentioned before, depending on the virtual environment you are in, you can provide stimuli for more of your senses. And this could at least potentially give a high amount of information to the user. And finally, something that is very important, I mean, there are some advantages, there are more than that, is that the engagement. So when the people are in a virtual environment, they typically feel very engaged, and this can lead to better remember their experiences, which is why virtual reality is a very good platform for education. However, we require to do something. So in general, one of the things that we need to do is we require higher amount of frame rates. So in order for the user to avoid the user to have severe sickness, we need to provide like 90 frames per second of sustained frame rate. And this is more than we typically achieve in a desktop PC, because we need to have like 90 per 2 eyes, which means something like 180 images per second, while in a regular monitor, we are generating like 60 images per second. Moreover, this generation of images, it has to be continuous and it has to have a low latency, because larger latencies can cause motion sickness. So we have to have these high frame rates at sustained frame rates without latency. And when we talk about latency, we refer not only on the frame latency, which is what the user is typically used to, so this thing here, but the full motion latency. Oh, I cannot change 1 second. 1 second. The pointer done. Okay, but full motion latency. So it includes the processing of the user input. So if the user moves, we have to update properly up to the final image that we display, we generate for the user immediately. Okay, so in the beginning of VR, we could find this kind of classical displays, but has made virtual reality more popular and consumer level are these affordable displays, the displays that were made popular thanks to the Oculus Rift that was developed by Oculus. Now, you know, it belongs to Facebook, because it changed something that was maybe $15,000 for something that was $350, something like that. So consumers can buy this, and therefore there is a bigger market for creating contents for this. But these head-mounted displays have also some limitations. One of the limitations is that we isolate. We don't know where the other people are. Of course, we can create one of the good things of virtual reality is that we can collaborate, but in order to collaborate, we have to render the other persons in the virtual environment in some way. They also have limited GPU power. Actually, they use the GPU. Most devices use the GPU of the PC, but they have to generate higher frame rates. So it's typically more difficult to render at sustained frame rates than it is for a desktop. They also come with some limitations in movement range, because the trackers are placed at fixed positions and you have like 2-3 meters where you can walk. And also, if you have the USB if you have the device connected by USB to the PC, you have the wire that does not let you move, okay? And it's kind of cumbersome for interacting. And although there are some alternatives that do not have this connection, their GPUs is less powerful than the GPU in a desktop PC. So then there are other compromises that we have to do. In order to interact, as I was saying before, ideally we should be able to interact as freely as possible. In general, this is kind of complicated. So some controllers have been created. And one of the bad things of these controllers is that they have less precision, for example, than using a mouse. They are also fatiguing because you have to move your hands in the air. And although there are some alternatives that do not use these physical devices and you can move your own hands, you have problems of precision, self-occlusion, and so on. And there's also another problem with the interaction, is that when you're willing to point some of the objects, the pointing device, just this one by HTC, usually generates a ray in order to point to the scene. And the object I want to select will be pointed, for example, by a ray starting from this point, but what I want to select is going to be seen from a different point of view by myself. So some occlusions problem may happen when you want to select something. Of course, there is a lot of research trying to solve this, but this is something that we don't need to take for granted. Okay. There's also some other issues related to how the displays are. So the displays are close to the eye, so typically they get dirty. If you wear glasses, maybe you cannot put them inside the device, okay? And they provide a large field of view in a small size. This this has a consequence that we have a relatively small resolution. So the number of pixels we have is smaller than in a monitor, but it represents a larger field of view. So you can see some numbers here according to a survey made by Steam, where they were asking their users which were the conditions in which they were working, and the more popular monitor had like 2K wide, 1K vertical, while the most typical VR device has only 1K horizontal and 1.2 vertical. And monitors typically have a 60 refresh rate, and as I was saying, HMDs have 90 Earth. So since the monitor will represent just a very, very small field of regard, and the intended field of view, the field of view of a HMD is more than 100 degrees, what happens is that basically for the same number of pixels, we have, or for the same angular degree, we have 6 times less number of pixels. And this has bad consequences. So the first thing happens is with text. Text requires much more space than usual. If you want to put labels, if you want to put menus, then you require more space in order to make this legible. Also, when we render data in the ways of charts, we also require thicker lines. So it means that the charts will be bigger. And if we render things such as meshes, node connections, again, we have to draw thicker lines, otherwise we have aliasing. So in general, when we are, let's say, adding a label or adding a menu, since it has to be big, it will occlude part of your scene. But there is a lot of applications that we can find in BioMed. I did this classification, but you can find many other things. So thanks to the characteristics of virtual reality devices, we can use them to explore large biological or medical models, making applications such as computational microscope, and doing things such as anatomic education. We also can take advantage of the interaction with the 3D models to carry out some tasks, for example, like the design of DNA models or surgery training. I'm going to talk about the surgery training application right now, and also intervention preparation. And also we can do things in collaboration with other people or without collaboration that are complex models that are easier to understand thanks to the 3D perception of the positions of the elements, such as molecular modeling or DNA design. So there are like different trends, areas of application that you find in biological data. For example, there's a lot of applications related to education, to understand cells, understand molecules, and so on. There's also applications related to interacting with molecules, such as molecular binding, for example, combining molecular dynamics with virtual reality interaction, because the easy perception facilitates the addition of the elements. Also, it's better to analyze 3D animations of molecular simulations because it's easier for us to understand the positions of the different elements, the ligands, and so on. And you can also edit models, for example, for refined models or correct molecular models. And it is also another task that can be done in collaboration. In medical area, for example, there is a lot of training that can be done in virtual reality. And training implies not only training for a certain surgery, but for certain procedures for dealing with a patient. Also treating with psychomotor skills, for example, practicing for surgery, and also emergency response, and so on and so forth. You can also plan a surgery. So there are softwares that help you determine which parts of the subject I have to cut or where I have to place one element. So it's also easier to do in virtual reality. And of course, there's a lot of potential in anatomy. For example, there's a lot of papers related to teaching anatomy to medical doctors or nurses or so on and so forth. So I wanted to talk about an example that I find it's kind of complex, and it's quite illustrative of the potential of virtual reality in medicine. So in this case, the example, which is this paper appearing here, is related to training novice surgeons in pedicle screw placement. Okay, so the idea is that for certain certain people, we have to have a deformation or have an important problem in the spine. Spinal stabilization through screws is the only way to go. And in order to do this, we have to plan properly. And the idea is that VR can be, or the hypothesis is that virtual reality could improve the creation and the duration of planning. And what they did, these authors, was experimenting what's the difference in learning if we train a group of novel surgeons with a virtual reality application, and we compare with the classical training that the other surgeons typically undergo. The idea is that they had this application. In this application, they have this haptic device that let them have the feeling of the insertion of the screw. And they also need a couple of first initial calibration in order to get the positions of the two elements and the position of the user. And once they have this calibrated, the user can start practicing by placing nails into the target positions with tactile feedback and image feedback that lets them know whether they are placing the screw in the proper position or not. And they compared taking a set of novel surgeons with this training. Well, this training is not the only training they do. They have the first theoretical training. They watch some videos, and the only difference between the surgeons was that one group of surgeons was doing this practical work in virtual reality, and the other one was doing the last step using classical training that was observing an experienced surgeon doing this and explaining them. And what they had there is a procedure that first they perform a series of CT scans of different cadavers to measure and to plan the insertion of these pedicles. So they calculate previously what's the size and the orientation of the pedicles they must be applied. You can see here an example of a scan with the pedicles applied. Okay, and during surgery, they ask the users to place the specimen first in prone position. They remove the soft tissue in order to make the vertebral body anatomy exposed, and they had to place 6 screws. Okay, after doing this, all the students did this, and they evaluate the result using a CT of the model with the screws in. And they measure the distances between the planned position and the real position where the screws were placed. And what they found is that the results were more acceptable for users that had trained in virtual reality, sorry. So 100% of the screws were placed properly, while only 79.2% of the screws were placed properly, an acceptable position, they say, by the students who had not practiced in virtual reality. Also, the placement time was much faster with virtual reality than non-virtual reality. Okay, so I think I'm going a little bit slow. Things that are limiting, so some challenges for medical visualization is the speed, because we need to render high speed, and biological models, cells, molecules have a lot of strangles, shape complexity, shading, dynamism, collisions, and so on, which makes this very slow or difficult to get higher frame rates. And the medical models have problems with memory, especially volumetric models. Also, the rendering methods are very intensive in GPU, and also things such as simulating deformation. So since the speed is something difficult to achieve, it's difficult to use this in medical. Also, the field of view is kind of complicated because we have larger field of view, which means that we need to render more elements. And also, as I was mentioning before, some of the elements that we would like to put, such as menus, labels, lines, charts, and so on, are difficult to fit because we need more space. So other problems come from the collaboration. You need to transmit the data, which can be difficult for remote. We can have firewalls and also memory requirements. And if we get low latency, we need to get low latency to avoid cyber attacks. So let's go for AR. So AR is aims to present information that is directly registered with the physical environment. So the key components in augmented reality is that they combine real and virtual. So the idea is that we enhance the real world. Again, we have to have proper update in real time. And one of the key issues here is that we need to register the real world in the 3D position with the virtual elements that we add. In some cases, this needs to be achieved without interruption because it could be problematic, for example, if you're performing surgery with augmented reality information. So as I was saying, interactive in real time means that we have to have this tightly coupled feedback loop so the user can move continuously like in virtual reality, and the information must be updated properly. So we need to track the user's location in real world, which means position and also the pose. This 3D registration, as I was saying, is necessary in order to augment the information. If we want to put a label of what an object is, if the object moves in the real world, we need to follow it. Okay, so everything must be in the same coordinate system, and this can be difficult to achieve depending on the technology you're using and depending on what you're trying to match. For example, tracking with these markers, it's pretty easy. It's not very costly, but it's intrusive. If we want to track freely, we need to try to monitor natural features, which can be a little bit more problematic. And in some cases, we require higher image quality in order to perform the tracking properly. So it's more costly. So in this case, we have these 3 elements. So we need a tracking system, a registration system, and a visualization component. And we need to have some database that stores the physical information of the real world and the virtual world in order to match them. So the semantics, for example. There are different technologies to achieve this. Some are see-through, where what we have is something like an optical see-through. We see the real world and we superimpose something. Or video see-through, which means that we record the real world with a camera, such as the camera of a phone, and we superimpose some information. But there's also new technology that it's intended to project information on your retina. And also, spatial augmented reality is basically when we create the virtual information on top of the real world using projectors. So the differences between these methods are on the degrees of occlusion that we are going to achieve, whether we are using real images or video images. For example, if we are using a camera and the battery is finished, what will happen? The image quality that we can achieve higher quality with our eyes than using an intermediate video device, okay? And also, this influences the technology, the transparency of the screen, the field of view we can achieve, okay? So the differences with virtual reality is that the virtual reality creates a virtual environment, while augmented reality augments the virtual environment. We want to still see the real environment and augment it with virtual information. So there's this continuum that people describe. I'm going to mix. And again, this was popularized quite a lot with Pokemon Go, okay? And also Google Glass. But the devices we use nowadays are this kind of Magic Leap or HoloLens. What are the issues with, what are the applications of these devices? So these devices have been intensely used in surgery interventions, for surgery assessment, for example. So to perform the intervention, to help perform the intervention to another person, or in education, for example. In biology, there's a less amount of applications that I've been able to know, for example, and then most of them, they focus education. And I'm going to introduce very briefly an application in biomed. In this case, it's the use of artificial intelligence, augmented reality in order to help in solving the problem of fibrous dysplasia, which is a craniofacial lesion where the normal bone is replaced by fibro-osseous connective tissue. The idea is that you try to reduce the bone in these parts. And it's very difficult to calculate the extent and the amount of the bone that has to be reduced. So what these guys did was to experiment with real patients' data that was printed in 3D, okay? And the procedure used a HoloLens in order to provide the augmented image, a surgical drill that was tracked, an optical tracking system that was tracking the surgical drill and also the 3D printed model, okay? And of course, they needed some markers to be fixed on the models in order to perform this tracking accurately. And the task was basically to recontour the first plant, and the recontouring plant was overlapped with the skull model. And the idea is that they had to perform the real recontouring with the model. Okay, this is how it looked like. All the menus were performed in such a way that only gestures of voice could activate them. Okay, and this is the plan, what they have to do, and this is the tracking of the drill that they were doing. Okay, in order to perform this, they had to perform a quite long learning process. Okay, but they found that the results were very nice. So they had a small discrepancy with the planning, which is say improve safety. So they don't provide, for example, numbers on how better is to real life, but they say it's better and also more efficient doing this, because other systems of providing information are difficult to apply and they lead to larger errors. For instance, not achieving proper symmetry of the skull. However, they say that the cost of the equipment is quite high, not only the HoloLens, but also the optical tracker they also need. Okay. And in bio, there's overall, I found a lot of education applications, especially mobile augmented reality applications, but mostly they show the 3D model and only some of them have some interaction. So just to conclude quickly, some challenges that we have in biomed is that we need to access the real world. So for example, these kind of structures, we don't have them in real world. So we can replace them with physical reproductions, but it's kind of more difficult to get this information. Also, subjects may be alive. So most experiments are with 3D models or cadavers, but if patients are alive, they can move. So this registration must be very, very robust. So to avoid, I don't know, patient breathing and so on. So there are other limitations related to the user interface that can make that some tasks to be more slow down. Okay, the perception of virtual environments in augmented reality devices is typically poorer than with virtual reality. Again, the registration accuracy is important. And in general, the application, the HMDs have much smaller field of view than virtual reality. So it's complicated to add them to the real life. You have only a small part where you can look and see the augmented information. And there are other issues regarding battery life, comfort, and so on. So to conclude, if you want to do something in virtual reality, we have to have low latency. There's a lot of possibilities of interaction and collaboration that can be exploited with respect to desktop. And in augmented reality, it's important to have this real world data, registration accuracy, and we are limited by the field of view. And with this, I finish. I was a little bit longer than intended, but I think it was more or less okay.
It was perfect. Thank you very much, Pere, for this tour through AR, VR in biomed for us. Actually, we are having a lot of questions here, and it's pretty clear right now that we won't manage to answer all of them live. But if you will have time, anytime within the day, to answer afterwards on Discord, that would be cool. But we will manage at least 2 or 3. So the first one is from Hanna Pokojna, who is thanking for the talk. And the question is, with the surgical training example, is there perhaps a difference between surgeries for which types this training approach is more appropriate than others? And then she also added that specifically in VR, soft tissue versus hard tissue surgeries.
Yeah. I mean, I wanted to put this example because in this example, one other element that I was not mentioning in the technology, which is the haptic device, was included. I mean, when you are interacting with the virtual world in virtual reality, you expect certain things to behave as a certain way. So, for example, training in medicine is very important, depending on the training thing that you do. But if you train surgery, for example, in many cases, it's very important to have a feeling that it's very, very similar to the real one. So if you really have to do, I don't know, for example, we did an experiment with some insertion in the brain, and we needed to mimic the exact strength that you need to exert, because otherwise you're going to do it wrong. But there's a lot of training procedures that do not necessarily imply having this fine a precision feeling. I mean, when you train procedures, what thing must be done in this case, in this order, in which order, or what tools do I have to take for a surgery, for example? You do not necessarily need to have this haptic device, but of course it depends on the surgery you're doing. It can vary quite a lot.
Perfect, thank you. So another question is from Alexander Kahl. And the question is, which technology do you think will be used more in the future? Visualization in VR or rather AR?
Well, one of the problems with augmented reality is that it's difficult to contrast the images. So if you want to do visualization and you want to put data, virtual reality seems a more adequate place. Although we don't have this enough resolution now, there are some devices with 8K that probably would give us enough resolution in terms of number of pixels so that we can put like small charts or charts that do not occupy the full view. So regarding, for instance, displaying data, I think that we need a lot of space because we always have problems of putting a lot of things with multiple views and so on. So maybe for displaying data, VR is more adequate. But for surgery, things that, I mean, if the battery finishes, you want the surgeon to still be able to see what's going on. So for some things, I think augmented reality is really, really very powerful because I mean, assuming that you can live without it, but there's this kind of thing that some of the features that provide are completely different ones from the other.
Yeah, thank you very much. It's really exciting, and I really would love to continue with this discussion, but I think we are really running out of time, and for the sake of a small break afterwards, I think we have to switch to another talk. So as I said, if you can still answer many questions which are showing up on Discord, that would be really cool. And thanks a lot once again for this great talk.
Thanks to you for inviting me.
Thank you very much.